Hello, my wonderful chemists. We are going to talk about solids today. So, chapters 11 and 12 talk about condensed states of matter. And condensed states of matter are solids and liquids, of course, where the particles are condensed or close to each other. When particles are close to each other, the intermolecular forces become significant, and we've talked about how those intermolecular forces affect all kinds of different properties like boiling point, melting point, heat of vaporization, and so on. So we're going to talk briefly about solids. Solids don't really get much respect in chemistry because reactions are what chemistry is all about, and chemical reactions happen when your molecules collide. And so in solids, the particles are stuck in place vibrating, and so it's very hard for them to collide. There are two main types of solids. There are amorphous solids and crystalline solids. Most solids are crystalline, but there are a few that are amorphous. Amorphous solids are basically solids that have a random arrangement of particles. Whereas crystalline solids, which are the majority of solids, are the ones that have a high regular arrangement or order, and they make a crystal. Therefore, they're called crystalline. So they have a high regular arrangement or order. So you have these ordered repeating patterns that you find. So examples of an amorphous solid would be like plastics, rubber, most other solids are crystalline. Excuse me. So within crystalline solids, the solids that form crystals, there are four different types. So there are crystalline ionic, crystalline molecular, crystalline network, sometimes we call those network covalent, and then crystalline metallic. So for each of these four crystalline types, you need to know these four things. So you need to know the basic structural unit of the lattice point. You need to know the forces within the cell, four properties for each type, and then an example. When we say forces within the cell, that means like intermolecular forces, basically, that are holding your particles together. Basic structural unit of the lattice point is what is at the points of the crystal, the lattice crystal. So let's start with ionic solids. All of these, by the way, are a review. The only new one is the network one, but last year we talked about ionic, molecular, and metallic. So let's start with ionic. So obviously these are made up of ions. So these are substances that are composed of ionic compounds. So your cations and anions are in there, and they're found at the lattice points. So the first question, what's found at the lattice points, is cations and anions. So basically, if this was my crystal, these are all ions. So if this was NaCl, for example, this would be the Cl minus, this would be the Na plus, and so on. Some general properties of these ionic substances is that they are hard solids. They're non-volatile. They have very high melting points, and therefore they are solids at room temperature. And usually their melting points are in the thousands of degrees, with a few exceptions. They're non-conductors of electricity as in the solid form, but once they are dissolved or if they're molten, then they conduct electricity. The reason for that is because they are made up of these ions, so positives and negatives, but those ions are kind of crammed together in that crystal structure for a net of neutral charge or zero charge. Once you melt them, the ions are able to slide around each other, or if you dissolve them, the water physically gets in between them. And so now there's separation of these ions, separation of charges, and therefore they can conduct electricity. Most of them are soluble in water, but we've seen from our solubility rules that some of them are not. So this question says, briefly discuss how the above properties can be explained by the Coulombic attractions or electrostatic attractions of the ions in the bonds. So we've answered the first question, which is what's at the lattice points. We've answered the third question, which is some properties. Let's answer the fourth question, which is examples. So any ionic substance that you can think of, NaCl, CaF2, NaHCO3. So anything that's ionic is going to be considered a crystalline ionic solid. And then the question that we missed here was, what is holding these together? And so they are held by electrostatic forces or Coulombic attractions, right? So what's holding that crystal together is the electrostatic attraction, also known as Coulombic attractions, between the ions. Let's just say between the ions. So you have an Na plus and a Cl minus. What is holding, that crystal together is the attractions between the positives and the negative ions that we see right here. So these are called Coulombic attractions or electrostatic attractions, which again mean positive and negative attractions. So this question is asking you, how does this attraction, how this force affect the above properties? So the above properties, that they're hard solids, that they have high melting points, that they're non-volatile. These are all because of these strong electrostatic force. So the particles are really attracted to each other, so they want to remain as a solid. They do not want to vaporize or even melt and turn into a liquid or a gas. So we'll say 1, 2, and 3 are just because of the very strong Coulombic attractions. Particles are so attracted to each other, they want to remain condensed as a solid. Property number 4 was that they are non-conductors of electricity while in the solid phase, but they will become electrolytes, meaning they will conduct when they are dissolved or molten. So what we just talked about, so we have these positive and negative charges, but they are packed in a crystal as a solid. And you get a neutral compound, right? Your crystal is all neutral. However, when you dissolve it or you melt it, the ions are free to move around, so then you get separation of charges and it can conduct electricity. So when molten or dissolved, ions separate and can move around each other. So when you get separation of charges, that allows conductivity. It allows electrons to flow, which is what electricity is the flow of electrons. All right, so these are ionic substances. Within ionic substances, remember we said these Coulombic attractions between the positive and the negative charges is what keeps the crystal together. So in order to melt an ionic substance, you got to overcome these Coulombic attractions between the ions. So this question is telling us the ions of NaF and MgO are isoelectric. That means they have the same number of valence electrons. And the inter-ionic distances are about the same. So one is 231 picometers, one is 210 picometers, so they're very close to each other. Why then are the melting points of NaF and MgO so different? So one of them is a little less than 1,000, the other one is more than 2,600. And so if you remember, these Coulombic attractions have to do with the charges, and then also they have to do with the size of your ions, the size or the radius of the ions, right? So the higher the charges, the more the attraction. Also, the smaller the ions, the higher the attraction. So in this case, they're telling us that their inter-ionic distance, so that basically is the bond length, or the radius, is about the same. And so it must be the charge that is affecting it. So NaF has +1 -1 charges, but MgO has +2 -2 charges. So having such high charges causes your lattice energy to be so high. So MgO has a much higher lattice energy because it has higher charges, +2 and -2 for MgO versus +1 and -1 for NaF. And so more energy is needed to break the crystal in order to melt. And so MgO melts at a much higher temperature. Okay, next one says, would you expect the melting point of CSF to be greater or less than that of CSI? So same idea when it comes to ionic substances. In order for them to melt, you have to overcome that Coulombic attraction, that lattice energy. That's the attraction between the ions. And so that attraction has to do with charges. It also has to do with the size or the radius. Higher charges, smaller sizes cause more attraction. So when it comes to charges here, this is +1 -1, also +1 -1. So it's not the charges that matter in this case, it is the size. And so both of them have a CS ion, so that's the same size, but the anion here is different. F- versus I-. F- is much smaller. And so because it's smaller in radius, the Coulombic attraction is stronger, the lattice energy is higher, and so more energy is needed to overcome that lattice energy in order to break the crystal and melt your solid. So let's write that down. So CSF has smaller size and CSI. Therefore, CSF has stronger Coulombic attractions between the ions and higher lattice energy. So more energy is needed to break the crystal in order to melt. Don't forget to actually answer the question. So therefore, CSF has a higher melting point. And when you're answering a question and then explaining it, you want to underline your answer, or say your answer at the beginning. So say higher. Oops, sorry. Say higher there, and then actually answer the question. So you would say higher, and then you would explain or underline it like that. Okay, so ionic substances form ionic crystals. Let's go to metallic solids. So metallic solids are obviously between metals. So examples would be any type of metal. So sodium, copper, gold, any metal really. So if you remember, metals lose electrons to become more stable, to have a noble gas configuration. And with ionic substances, you have a metal and a nonmetal. So the metal loses the electrons, gives the electrons to the nonmetal. But here, there are no nonmetals to gain those electrons. So the ions, or the metals, become ions. They give away their electrons, but then nobody is there to take those electrons. And so if you remember, we say we have these metal cations in a sea of electrons. So let's say you have sodium, for example. Each sodium loses an electron. So they all become cations, but then the electrons are there having really nowhere to go, so you have these metal cations in a sea of delocalized electrons. So the metal ions, the cations, occupy the lattice points. So if you have a crystal, the points there, those are cations. Those valence electrons then are delocalized. That means they're not in one location. They move around in the crystal and in these orbits, and these orbits are called conduction bands. The attraction here, what keeps this all together, is the attraction between the positive cations and the negative sea of electrons, or sea of delocalized electrons. They like the word delocalized in College Board. So we answered the first two questions. Third question is properties. So metallic substances, they have very high conductivity, whether it's heat or electricity. They will conduct electricity even as a solid, and that's because of that sea of delocalized electrons. Remember, electricity is the flow of electrons, and so you already have electrons flowing here, and so that contributes to the conductivity of metals. They're usually shiny. They have luster. That's because of the photoelectric effect. So the idea that those electrons absorb energy from light and then they jump up to high energy level and you lose those electrons, giving off photons of light. They are non-volatile. That's because there is such strong attraction between the positive cations and that sea of electrons, and so they are non-volatile. They're solid at room temperature except for mercury. It's the only metal that is a liquid at room temperature. So they have pretty high melting points. They're not as high as ionic solids, but they have pretty high melting points relatively. And they're insoluble in water and in all common solvents. To go along with metals, you can combine different metals physically to make an alloy. So alloy is a physical mixture of metals, and usually you make that by melting two or more metals together. Alloys are usually made because you can make them better conductors, you can make them more resistant to corrosion, so you can kind of like make them into whatever, make a combination of whatever metals you want in order to make better properties, basically. Just like pure metals, they have these cations in a sea of delocalized electrons. So it's the same idea as metallic bonding, except you have different metals in there as opposed to one type. And alloys always have a lower melting point than either of the pure metals. Any mixture will always have a lower melting point than the pure substances. I remember when I was both a student or a TA for organic chemistry, we used to make, most of our labs were synthesis labs where we would make these compounds. And as a TA, I would collect samples from every student, and part of their grade was the purity. And so I would check, make sure it's dry, make sure it's the correct color, but then also I would check the melting point. And if the melting point was lower than it should be, then that means there's a lot of impurities. So mixtures will always have a lower melting point than the pure substances. There are two types of alloys, and those are mentioned by name in the CED. which is the curriculum for AP Chem. There are interstitial alloys and then substitutional alloys. So interstitial look like this, where you have two drastically different sized particles. So you have larger sized particles, and then you have smaller sized particles kind of in the middle, in the gaps between the large particles. An example of that would be like steel. So your larger particles would be the iron, and then you have some carbon trapped in there. And so small atoms fill the spaces between the bigger atoms, making the alloy more rigid and less malleable than the pure metal. So again, steel would be an example of the interstitial here. Substitution alloys, from their name, you substitute. So your particles are about the same size. You're just substituting some atoms for another type of atom. If you think about it, like let's say you play sports. Let's say you play soccer, and let's say your goalie gets hurt. You're going to substitute that goalie with another goalie. You don't want to substitute it with like a striker, right? So whenever there's a substitution, usually we try to make the thing that's substituting the original very, very similar. And so when we say substitution, that means that the particles are pretty similar, and in this case we're talking about size, similar in size. So something like brass, that would be an example of a substitution alloy, because copper and zinc, oh, there's a lot of P's here. Copper and zinc are very similar in size. And so the alloy of brass, where you melt copper and zinc together, kind of looks like this, where both of them are about the same size. You're just substituting one type of atoms for another. Okay, so we covered all four things. We covered examples. We covered what's at the lattice points. We covered what attraction holds the crystal together, and we also covered some general properties. So the next type is molecular solids. So another word for molecular is covalent. So these are solids that are covalently bonded, and they consist of discrete molecules. So if I have an ice cube, for example, that crystal that's made by my ice is made up, you would find water particles at these lattice points. So the lattice points have discrete molecules. If I look at an iodine crystal, then I2 molecules are in that crystal. If I take dry ice and look at what's at the lattice points of the crystal, that would be CO2 molecules make up the crystal. So whatever molecules that covalent substance is made up of, that's what's at the lattice points. The attractions that hold the crystal together are your regular intermolecular forces, which range between either hydrogen bonding, London dispersion, or dipole interactions. So those are your attractions that hold the crystal together. We already said molecules occupy lattice points, and some examples would be like I2, like we said, sugar, CO2, water, obviously those in the solid form. Some properties for molecular substances, they are non-conductors with the exception of acids when they're dissolved in water. So something magical happens when you put an acid, even though it's in molecular. When you put it in water, it ionizes and you do get conduction, but that does not happen with other molecular substances. Most of them are insoluble in water, but there are some polar substances that are soluble. They are volatile. They have a little bit of vapor pressure, depending on what type of substance it is. They will have at least some type of measurable vapor pressure, and they have low melting points and boiling points compared to other types of substances. So the lowest melting and boiling points are molecular substances, followed by metallic substances, followed by ionic substances, and then network covalent, which we'll talk about in a minute, have the highest melting points and boiling points. So let's look at this question. It says, in a molecular solids, how do the intermolecular force strengths or the covalent bonds compare to the intramolecular, how does it compare to the intermolecular? So the intra, so the bonds are much stronger and harder to overcome than the intermolecular forces. So those would be like the H bond, dipole, and London dispersions. So much easier to overcome these intermolecular forces because they're much weaker. So easy to vaporize something versus to break its bonds and actually, form a new substance. And then the last type, which is kind of new this year, is network covalent substances, also known as atomic network, depending on what type of substance you're talking about. There are only a few network solids, and the examples that you need to know about are silicon, quartz, which is SiO2, diamonds, and graphite, which diamonds and graphites are both just carbon. So these crystals are often called macromolecules because you have these huge either molecules in SiO2 or atoms, huge number of atoms in either diamond, graphite, or silicon that are kind of bonded together with a covalent bond, with an actual covalent bond, which is not something that we normally see. So this is the structure of diamond, and this is graphite. These are all carbon atoms. So at the lattice points, you have either atoms or molecules, depending on what it is. So if you have graphite, diamond, or silicon, those will be atoms, either silicon atoms or carbon atoms. If you are talking about quartz, then you'd have molecules, SiO2s, at each of these lattice points here. So in this case, we're talking about carbon because we're talking about diamond and graphite. And you can see that these carbon atoms are bonded together, and they're actually bonded with a real covalent bond. So these are not like intermolecular forces, these are actual bonds, covalent bonds. And so you can imagine these are very, very, very strong because they're actual bonds, as opposed to like hydrogen bonding or dipole or London dispersion. So because of this, these substances have extremely, extremely high melting points. It's so hard to actually break a real covalent bond. So these have melting points way higher than 1,000 Celsius. They are insoluble in any type of solvent. If you think about it, sand or quartz or diamonds or graphite or silicon, they don't really dissolve, right? Some of them are brittle and some are kind of hard. They are poor electrical and heat conductors. So it's not that they're non-conductors. Some of them actually conduct just slightly. And we have this covalent bonding that is binding, holding these atoms together. Very, very, very strong. They have very different properties as well. You can tell, diamonds and graphites are very different. So you can see diamond has this like 3D, very intricate bonded structure. That's why diamonds are super hard. The very expensive knives have like a diamond tip on them. It's very hard to cut diamonds. You have to have like a laser to cut diamonds. Extremely hard. Versus graphite, which is in your pencil lead, is very soft. And as you write on your paper, these sheets of graphite come off because the way that graphite is made is you have these carbon atoms that, yes, are covalently bonded to each other, but they are flat. They're like kind of planar. So you have all these layers on top of each other. And so as you write with your pencil, these layers start coming off on your paper. And that's why you can write with graphite. So let's answer this question here. It says both graphite and diamond are carbon network solids, account for their very different properties. Oh, we just talked about that, right? So with graphite, you have these layers, and so that's why graphite is very brittle, and the electrons can actually jump from one layer to another, and that's why it can conduct electricity, versus the diamonds. They have this intricate 3D structure that is very hard to break, and can't really allow for movement of electrons in there. So let's write the answer here. So graphite is made flat layers of bonded atoms. It is soft and brittle. As these layers come off, and then electrons are able excuse me, to jump from one layer to another to allow conductivity. Whereas diamonds are very hard because of the 3D bonding in the crystal. All right, so I wanted to summarize all this for you, the types of solids here. So I have, remember there's amorphous and crystalline. So the 4 types of crystalline solids are ionic, metallic, molecular, and network covalent. And so the 4 things that you need to know about them are what's at the lattice points, what are the forces of attraction that keeps the crystal together, some properties, and then some examples as well. And so I kind of summarized the last couple of pages into just one table here, so it's easier for you to see and compare between the different types of solids. And the last box here says AP test questions expect you to be able to relate observed physical properties such as melting points, boiling points, electrical conductivity, hardness, and solubility to the type of structure or bonding present. So you want to focus your review on the relationship between the structure and the properties. You know, and we've talked about this throughout the lesson today, but for example, when you talk about molecular solids, why do they have such low melting points compared to the other ones? That's because the attractions between your particles are much weaker. You have either London dispersion, dipolar hydrogen bonding between those particles compared to you know, real covalent bonds, or at positive negative attractions between sea of electrons and the cations, or attraction between real positives and negatives between the ions, for example. So you kind of want to compare these properties with each other, and these properties are based on the type of bonding and the type of attraction that keeps your crystal together. All right, I hope you guys have an awesome rest of your day.